One guy, grad was you deal with light bulbs. They put it in the light bulbs. You just
Put it on a burger for the drive-through. I turned in my quiz on Friday.
Oh, same for me too.
So what is this being done? This is the exam?
Yeah, and I've had my homework.
Stop giving homework and quizzes so that I don't have to grade them. I wish I could say.
No waves like
Thank you. Yeah, just keep it here. Yeah.
Where's it from? It's 7 months. It's interesting.
Oh, we have.
There is.
At the C8 part of it. But yeah, they will do the video. We're there. Yeah. So that's 2 years. Then the old one, where we have a very more system. Well, using the sense of the or you want to put that on the first perspective. Euros. Everything you got. This is this. Yeah, I know it's gonna be something. Yes, something like that.
When is it on its way?
But from who's that?
She is also on it.
How was the midterm exam? Any comments or anything on that? Are they reasonable?
Yeah, I made a
Yes.
mistake on one of them.
Huh?
Yeah, I made a stupid mistake. Not even stupid. I just for some reason wrote the like in problem 4 the
Green's functional?
no, that's problem 3. Problem 4 was the evaluate the integral.
Oh, yeah, integral, yes,
I
yeah.
for some reason wrote the t to the L as like trying to write it as the r greater over r less than, and
Oh, okay, yes.
I thought
everything else.
the orthogonality relation or other equation we made it, that should be in the question.
Yeah, that should have been there, but then I felt that if I give that alone, then that would be a big hint, right, to it. I wanted to know that you know how to do integrals with this, yeah. If you'd asked me, I would have given. Yeah, but most of you remembered it. That was not the, I don't think anyone got or could not proceed because of that. But that would have been a big hint that, oh, that is what we have to use. Yes.
Did we talk about impulse momentum conservation in class?
No, that's expected, right?
Okay. I just for some reason have never seen that. And
Oh, maybe it's called conservation of momentum.
Mhm.
Forget the impulse part.
Okay.
Conservation of momentum is valid only when the total impulse is 0.
Okay.
So unless you use that, you cannot use conservation of momentum. So it's
Gotcha.
just sometimes I don't think it needs to be called impulse momentum conservation. It is Survey and Jewett textbook that I uses this terminology. And once you start using the textbook, you start using it. But I think historically it was not used. I was not familiar with it until I started using this textbook. So conservation of momentum. Same thing with conservation of energy, kinetic energy plus potential energy is equal to zero only if the work done by the non-conservative forces is zero. So it's called work kinetic energy theorem. So that should be okay.
think I need to go study some more linear algebra for problem one, because when it said make an eigenbasis, it's like.
Oh, okay,
I
okay.
didn't know what that meant really.
Again, that's terminology. I might be using it a lot. That might not be common. And you
Oh.
would just say complete set of basis vectors. That's it.
Oh, I've heard that before.
Yeah, that might be a more standard language. But again, those things, at least my argument would be that just that language should not affect you. Should, from the context, you should be able to figure out. Yeah, but surely it helps to be confident in what I'm asking, and then the person who is attempting it.
Sure.
I agree. I agree.
I'm also confused on question number one. Struggle to prove the signal X itself.
Right, yeah. Yeah, we spent very little time on it. That's also a big. You don't get to spend sufficient time to learn the vocabulary. So I agree to that. Rocky, Tanya, reasonable, right? So I was very hard on the grading, if you noticed. Harder than then my goal was that I'm giving 40% of the grades for the midterm to the in-class. So 60% will be take-home part. And that I will be very lenient, however, exceptionally lenient. So it should be very easy to get 60 out of 60 in the take-home. Unless you make some significant mistakes. So take-home part was hard, I'll be lenient. So it should be possible to get 60 out of 60. Plus the 40%. I think that will make it easier than what I usually do. So that was my intent. And making it hard grading also gives you a sort of a wake-up call that, okay, we don't understand the concepts as good as one should. So that was my overall intention for it. Okay. Reasonable? Yeah. Okay. Quiz. Oh, take home public. That's in one page?
No, this is.
Oh, that's a quiz. Yeah. Sure.
Sure.
Oh, no, take your time. Yeah. Who's that coming? You don't know. You wait another minute or?
See if she needs the bus, this one, then she will be 30 minutes late.
Okay, so we'll proceed and.
Just make the take on part right now.
Oh, anytime, yeah. If you want, you can submit it later. Don't delay too much, yeah, within. Yeah. Homework 10, I realize I have not posted yet. But will be due Monday. The final exam. Yeah. It's the last day of the final exam week. It's in the early morning. Exam will be usually exams are held in the same classroom as the class is held, so it will be good.
For the final day, can we request for 10 to 12?
And why is that?
Because we can review at the morning.
Oh, no, that is not a good enough reason because there are strict rules by the university that exam week, you cannot change the exams. And that's primarily because, let's say there is a class of 100 students And one student gets affected by that. So you go by the university rules and let's stick to that. Even if you have to change it, apparently everyone has to sign on it, which is not necessarily the best thing because
Yeah,
sometimes
that's
people don't speak out. So if it's not a serious thing, let's just stick to the. There might be a good component of the take home part. I was satisfied with the amount of work you put in into midterm 2. The scores might not tell it, especially with my hard grading, but I felt as if you guys were trying. So that makes me be lenient from this point to the final exam. So that might be a good bit of take home part in the final exam, but we'll see. So keep working hard and it stays like that. But
Yeah, when I solving homework, I saw video, you put some link in 2023 fall. The mid two and first video was about that, mid two and final both was take home.
correct. Yeah.
Yeah.
So often when I'm, if everyone is working hard, then I will make it all take home. That is, then exam is for me a take homework. So I teach in the exams. But sometimes when I feel that there is no correlation between how much you're doing in the class and the exams, then I have to. So exams are a way of making you work in a sense.
What is the prospect of a post-semester breakfast meetup?
Oh, sure. Yes, very much. Plan it. So the suggestion is that I think it comes from last semester. Last semester we went for a break. No, it was on the day of the exam, right?
Yeah.
Yeah.
Okay. Yeah, on Friday, I think we went for a breakfast, all of us, and then came and took the. No, it was a take home, right? Yeah. So it was due during the breakfast. So that was so that was the idea, I think. Yes, sure. We can do that. I'll save the money. For that, yeah. Yeah, let's do that. Yeah. So
Yeah, it was nice. I'll have some coffee in the morning, it's so good. Arbo's coffee is great. Is that?
so you would prefer breakfast or because there is an exam, which I haven't decided that this is take home. You cannot write the exam during the. So you want to make it a dinner instead?
That'd be nice.
That
Oh,
would be
yeah.
nice, yeah.
Is that are you guys all open because it's a Friday evening?
Yeah, we are.
Yeah.
Oh, yeah.
There is nothing better to do than have a dinner with your professor. You guys don't have that great life. Okay, so yeah, we can aim for that. Okay. So Friday dinner, I think it might be crowded because Saturday is commencement. So find a good spot.
This time.
No, Friday the
December 12th, yeah.
Where are you leaving? Pradeep, you said you might be traveling.
I'm planning, but no, I didn't buy ticket yet.
This Friday plan. Anyway, we have
Yeah.
time, so let's talk about that. Yeah.
Because I have to change my plan due to the in-person exam.
Yeah, sorry. Yeah.
Otherwise, my plan was back on November 23. And then take all the class from June.
That sounds so bad that an exam is affecting your life in a sense. Right?
Then I switch everything.
I might have plans Friday night.
Okay, so what do we do? Friday morning or Thursday?
I'll let you know.
Yeah.
And then we can decide.
So let's try to accommodate everyone. What other exams? Who else is taking another course? E&M. Is this all E&M?
And
Who
then-
else? Who is taking this and other than this course and the electromagnetic? Oh, what is this course?
Quantum two.
Oh, quantum 2. So when is this? When is the exam for quantum 2?
I don't know.
I think that should be 12 in the last day for the exam.
I can look.
I have to pick this call. I'm sorry.
What?
December 7th, What time do we have quantum?
It's Tuesdays. It's supposed to be Tuesdays from 1 to 2:15.
Something like that, yeah.
Usually he take the exam in the same time and then he'll not come on Friday. But Tuesday and Wednesday.
It's supposed to be Thursday, the 11th at 2:45 to 4:45.
Today,
For quantum,
Thursday,
Thursday afternoon. And then E&M, we have it
10 December.
Tuesday, it's December 10th.
Yeah.
Yeah,
Thursday, Thursday,
from 2:45 to 4:45.
Friday,
Yeah.
okay. Accept me.
We'll figure it out.
I think exam is on, for all the exam are before.
Before.
Yeah, the other exams are Wednesday and Thursday.
So this might be a good enough incentive to make it take home.
Yeah.
It sure helps.
So this should be the strategy students should have, or they could always ask for a lunch or dinner and then, oh, that we should make it. Take home. Okay, yeah, we'll talk about this more. And you should talk more because you will have the coordination better. Okay. We want to do spherical harmonics today. What is spherical harmonics? So you're taking electromagnetism, so you've probably seen this.
Which is to like the radio, product for like use like radio or something.
More.
My perspective of it is that spherical harmonics are the eigenvectors of angular momentum in spherical coordinates.
That's correct. Eigenvectors, he said, are eigenfunctions for angular momentum, but how does that help? What would you use it for? Like those eigenfunctions, like Fourier eigenfunctions. What do you do with them? Like what's the purpose? What's the point?
Like transforming. Like a common usage is transforming differential equations into algebraic equations.
Correct. That's that's very sophisticated application. But one more way of saying it is, that's correct statement, is that any function which is, let's say, x dependent, if it is going between minus infinity to plus infinity, maybe this is Fourier, right? Fourier. Eigenfunctions are e raised to I k x, right? And x goes from plus infinity to minus infinity. This means that give me any function that I can define on a number line. Right? We have 3 number lines that defines our space. So any function f of x can be written in terms of e raised to ikx. And it will have amplitudes. It's like saying music can be written in terms of frequency. Give me all the frequencies and I'll provide sufficient amplitudes. I can get any sound out of it. So similarly, give me any function. I can use the Fourier eigenfunctions to write the function in terms of. And the amplitudes for that, that you want to provide is called the inverse Fourier or Fourier components. That's what we call it. Okay. Like this is like a vector. Give me an eigen space, and I'll give you the components, right? AI times EI. But if you have the eigenvectors, these are the amplitudes which are called the components of a vector. These are the eigenfunctions. These are its components. If you know its components, it is usually unique. Not usually, it is always unique. You know the function. You don't have to talk in terms of a function. If you know this, that's as good as knowing the function. It's like saying music. If you know the tones of that create that sound, then that's sufficient. Is that clear enough? Now, you do the same for what spherical harmonics means is this is in X. Now, if you're on a surface of a on on the surface of a sphere. So your function is on a surface of a sphere. Where does this come up? If you're looking at the sky, that's basically the surface of a sphere we are talking about. We talk about angles and theta and phi. So here we want to talk about y, Ln. These are the eigen. These are the spherical eigen functions, if you want, and theta goes from pi 0 pi. Oh, is that miss the bus?
No, I emailed you.
Oh, sorry. I didn't check you. Okay, that's good. Yeah. Okay. And any function f of theta phi, exactly like this, but now you're on a sphere. Any function can be written in terms of, we expand in terms of L, has to go from 0 to infinity. This is very much like the hydrogen atom eigenvalues. You call it eigenvalues? What do you say? The energy level, quantum numbers, right?
Oh, yeah.
So the magnetic quantum number and the, what is the L called? What is the L called and what is M called? M is the magnetic quantum number. L is called angular momentum quantum number. So that's your angular momentum quantum number. And again, you M is equal to, now it goes from minus L to plus L. Again, the eigen functions L and theta phi. And you need F tilde. This time it is Lm. Oh, yeah, that's so these are discrete, so you write it below. So here it is a continuous variable k, all k's come into picture. Here L is discrete, so usually you write it below. So these are your amplitudes. Okay. So we have to first of all motivate that. We have to talk about what the eigenfunctions are, but that is our goal, right? You should be able to write any function in terms of that, and there are integrals, very much like the exam problem that you have. You can work on integrals. Most of the electrostatic problems, whenever there is a spherical symmetry, whenever you see a sphere, you will expand it in terms of theta. But anything that is defined on a sphere, even our a sky, that is basically a sphere, you will see spherical harmonics show. So that's the motivation. So let's go back and look for what, how do we go about finding these eigenfunctions. We need a complete set. So go back to the Laplacian. And Laplacian, because spherical harmonics were discovered by Laplace, and not very surprising. Once Newton gave his equations, you are interested in planetary motion, and 1 over r is a potential. We already saw legendary polynomials. We were working with 1 over r potential. Same idea here. We look for what are the solutions to the Laplacian. So what is the Laplacian, by the way?
Divergence of the gradient.
Divergence?
Divergence of the gradient.
Divergence of a grid. Yes, that's correct. So this operator, that's called the Laplacian. So that's equal to the Laplacian. That's just a name given. Right? In electrostatics or Newtonian physics, that's the equation that tells us that there is a charge, and you look for the electric potential. Give me at least one solution for this. Let us say I have so let's say I want to look for del square times phi is equal to our charge density will be, that's your rho over epsilon, right? So that's rho over epsilon naught. Let's make rho a point charge. So that's q over epsilon naught times q or minus r prime, where r prime is the position of the charge. What is the solution to phi then? if I say this is this equation I'm interested in, what is the solution to phi? The solution to this equation?
1/4 epsilon naught q by r.
Q by R, 1 over R, right? That's a potential. So notice all of you should be able to answer this. It says that this is a point charge. The moment I say rho is equal to a point charge, the question I'm asking is, what is the electric potential for a point charge? It's very physical. Mathematically, of course, you can go through the whole analysis and get the solution. But since you have done enough electricity and magnetism, you say this is a point charge. I know what the answer is, so you immediately say then that phi r is equal to q over 4 pi epsilon naught and 1 over r minus r prime. The moment you have this r minus r prime structure, there is what can you say about it? There is a translational symmetry in that. Whenever you have x minus y coming up as a function, that means that if I were to move the coordinate system, r will move, r prime will move, and there will be no difference at all. It's like saying I have a charge and I have a field. If I move the charge and I also move with it, then nothing is going to change. The whole universe, if it is translationally symmetric, if I move the observer and the source in the same manner, then nothing changes. If I move the, it's like saying that if I move the whole universe, assuming it has a boundary by about 1 meter, probably we won't see it. That's assuming that whatever is outside of the universe there is nothing in there. So if there is nothing in there, if I move the universe, it cannot affect my observation. So that's the kind of symmetry we are talking about. It's called translation symmetry. But that can be said in the following way. Let's say there is f of x plus a. So that can be expanded as f of x plus a. Okay, so a over 1 factorial times df by dx plus a square over 2 factorial times second derivative of f with respect to x square, or so on. Right, that's a Taylor expansion written in a certain form, and you immediately see that this can be written as 1 plus a over 1 factorial plus a square over 2 factorial. The whole thing acting on a function f of x. If you notice, this is something is wrong, right? There's a d by dx I missed. This is nothing but an exponential expansion. So I can write this as a series. Let me run it from L equal to 0 to infinity. And it is a raised to L. No, it is a d by dx. 1 over L factorial, a d by dx. Is that clear? Any questions on that? So f of x of a always can be written as an operator expansion function. If I have a function that depends on 3 dimensions, r plus a vector, it basically becomes the derivative becomes a gradient, vector a becomes a vector, and what I have is L equal to 0, infinity 1 over L factorial, and this time a starting with the gradient. Let's do now. Yeah. Thanks. Oh, right? This will be sort of the key to expanding our, so when I say I want to expand in terms of this, I'm interested in what are these eigenfunctions somehow. Yeah, I can expand a function in terms of f of r, f of r. Yes. So if that is the case, if I were to apply this on the electric potential, what I learned is that 1 over r minus r prime will be equal to summation L equal to 0 infinity 1 over L factorial. And now instead of a, it is minus r prime. And what will come here? I'm using this equation to rewrite this. In terms of that, so what will be on the right side?
1 over r.
1 over r, right? Because the magnitude of this, so it is r prime is equal to set to 0. So it's just 1 over r. So the claim is that if this is equal to 0 everywhere except r equal to 0, right? That is an infinity at r equal to r prime, right? And otherwise, the expectation is that it will be a solution to the Laplacian. So let's check for each L what happens, just for having an insight on what is going on in here. So let's begin by 1 over r itself. So L equal to 0 is 1 over, so we are looking for this quantity, or maybe, yeah, let's call this the following, right? VL. Why not count? Yeah, I'm not sure about the constants that are going to come out. This is the spherical harmonic itself, except for the m, but I'm just not calling that. So VL is equal to minus r prime. So that's just each term in there without that L factorial. Factorial also, right? Why not? Just a label I'm using. So what about L equal to 0? There is no operation, 0 factorial is 1. So VL is equal to 1 over R. And let us ask, so V0 then is equal to 1 over R. What about the Laplacian of V0 is equal, let's put a minus sign because then it is the Maxwell equation, right? So this is equal to minus del square of 1 over R is equal to, what is that equal to?
To active,
Again?
next to active.
No. No. Use physics. Try not to do derivatives. Look at this equation and try to interpret what's going on. 1 over R is the potential. What is the gradient of the potential? It's the electric field. Divergence of an electric field is the charge density. Right? So what is the charge density associated with 1/r? It's a point charge, so it should be 0 everywhere except at the point charge itself. So this is equal to 0 everywhere unless r is not equal to 0. If r is equal to 0, it's a delta function, so it is infinite. Notice I did not do the math. That's harder to do that, but it's expected that you know how to proceed with that. Is that clear how I went with it? 1/r is electric potential. Gradient of that is electric field. Divergence of electric field is charge. So I just have to look for what charge gives me 1/r. And that's a point charge, which is 0 everywhere except where the charge itself is. Okay. So okay, so that's L equal to 0. What about L equal to 1? So V0 now
V1,
is equal to
V1,
oh V1, yes. That's correct, sorry. 1 is equal to 1 factorial is 1 itself, so it is minus r prime dotted with gradient of 1/r. What is that equal to? This is the electric potential due to some charge distribution. And what is that? Let's say evaluate that gradient of 1/r. How do you do this? So you pretend that this is like a normal derivative, so it is minus 1/r square. So that's minus 1/r square. And then you take the gradient of the argument itself, that's r hat. So this is equal to r prime dotted with r hat over r square. What I've used here is that the gradient of a magnitude of a vector is equal to r hat. So that we did that somewhere in the first couple of weeks when we were working on. Is that clear how I proceeded? I pretended as if I'm doing a normal derivative and then it's a chain rule basically. And then I used this fact. Write this as r prime dotted with r over r cube. The moment you see 1/r, you know that that is a electric potential due to a point charge. Is this by any way how familiar? That's a dipole. That if you're familiar with the electric potential due to a dipole, that's the electric potential due to a dipole, and r prime should be interpreted as the dipole moment itself. But here it is a position that is coming out, but that's just a mathematical, you just have to interpret this to be a dipole P dotted with r over r cube. And a dipole, and that not just a dipole, it is a point dipole. So a point dipole is a positive and a negative charge in the limit when they are together. So this is a point dipole in the following sense: negative sign and a negative charge and a positive charge. So this is Q, that's Q minus n plus Q, and there is a distance between them, which is, let's say, A. Right. So a point dipole will be, so P is equal to A times Q. Sorry, this is a normal dipole. A normal dipole is equal to distance times the charge. But now you do the following. Take the limit A tends to 0, Q tends to infinity. So this is very small, that's very large. But you do it in such a way that the product is the same, or product is fixed. So A times Q is fixed, which is a dipole moment. So it is practically bringing negative and positive charge together. Or you can also think of this as a derivative of a delta function. A dipole moment has charge density. Here the charge density is, where was it? Here the charge density is just a delta function. Take the gradient of a delta function, that's your dipole moment charge density. You can take first derivative, second derivative is a quadrupole moment, or a point quadrupole moment, third derivative will be L pole, so you can keep doing that and you get all the multipoles charge distribution. So if that is that's a dipole moment, then you know that del square of V1 is equal to 0 again, except when R is not equal to 0. But that's maybe I have asked too much from you that I said that all this algebra works. So that is another nicer way of looking at it. If I have to show you that V1 is actually a solution of this, I just have to show you that this is equal to 0, except at one point. So that usually works out much easier. So you have del square times V1 is equal to, this is R prime, so I have a minus of square, and I have, now I'm doing minus and a minus, so make this plus, and we have R prime divided with del of 1 over R. Right? So this is, I've simply written V1 expression in there. I've not done anything yet. These are three derivative operations. R prime doesn't care for the derivative, right? This is a derivative with R. R prime is a constant. Partial derivatives don't care for any other variable except for the variable you're taking the derivative with. What is the, if I were to replace two derivatives, that means to say maybe d by dx. D by dx of d by dy is always equal to d by dy of d by dx. If we work in that regime, otherwise integrations will not be allowed. So this gradient operator can go through because it's another gradient operator. These are like using partial derivative commutation. So this can go through. So I can bring that out, R prime times or the gradient, directional gradient, and the Laplacian of 1 over R. What is the Laplacian of 1 over R? 0, that we already showed, except for R equal to 0, it is equal to 0. Otherwise, it is a delta function. That's the best we can say. So this is equal to R prime. So there's a negative sign to that. So this is negative R prime after the gradient, and this is delta function, or minus R prime. And there will be a 4 pi also. I'll be precise, that will be a 4 pi also in there. That's what I meant by, remember, whatever this is the charge density for this potential. How does the charge density look like? There's a dipole moment and a derivative. Right, so charge density for a point dipole is the structure. Your derivative of two remember, two charges means derivative, right? 2 points f of x and then f of x plus a, then you bring it closer, that's your derivative. Do the same thing for L equal to 2. You can show that this will work for any L square of V of L, but let's not even go for L equal to 2. But just any L, right? So any L, this will be equal to del speed minus del square, and then there is minus 1 raised to L. Second part of right, that's minus 1 raised to L, sorry. And right, this is minus R prime. And there was an L factorial here also. 1 over L factorial. This can go through that. Again, you have derivatives. You have minus R prime. It is equal to so this then is L4. This is a dipole, L equal 2 will be a quadrupole. This is the charge density for an alpole. The charge density for N or an alpole, N or a A, right? For A alpole. So that's the I. So this structure seems to be very important for the construction we are making. Again, notice take any function which is translationally symmetric, expand it out in terms of the gradient operator, and it seems like they will always be satisfying the Laplacian. And if they satisfy the Laplacian, then in principle, any functions that satisfies the Laplacian can be written in terms of these functions. So let's look for one more pattern in all this. So it seems like this is our 1 over r, right? 1 over r cube, 1 over r raised to 5. And it is not really r cube. If I were to take out an r magnitude from here, r square, r cube. So these are all powers in 1 over r. What over the opposite is there a expansion in r itself? So let's ask if the following is true. So let's say minus the Laplacian of a vector A dotted or r prime, right? Instead of r prime, I'm saying A times r. Is this a solution to the Laplacian or not? Is this equal to 0 or not? So let's take the operation in here. So this is negative gradient of the gradient of the divergence of the two gradient operators, and let me write this as r dotted with A. So this is acting on these two quantities. So everything, it's acting on everything on the right. And if you recall, how much is this equal to? So a gradient operator acting on a coordinate vector. Yes. R hat, no, that was, remember, that was different. There's a slight difference here, right? There's a gradient of, there is no vector sign on that. That's a length of a vector. Now this is a vector itself. Right? What is that equal to? If there was two identities, you have to remember if you're working with vectors, the whole of vector algebra is one, right? It becomes trivial, all of the. So this is one. It's good to remember because in terms of these two identities, once you prove that, then the whole of vector calculus becomes sort of straightforward as far as algebra goes. So that's equal to 1. So this is equal to divergence, and then there is 1. Then there is a 1 is basically identity. This is equal to the gradient of a constant vector A. So gradient of a constant is 0, so that's equal to. So this satisfies the Laplacian. Like we are now looking for higher powers, right? There was 1 over r square, 1 over r cube. We are going in the opposite direction. So let's try the next one. Is this satisfying the Laplacian? Now we already did it for 1, so this will be the same as how do you do this? Is that an easy way of doing this? Let's just do it, right? So minus first do the gradient, and is A dot is the R whole square. Do the first gradient. dotted. Yeah, this is pretend that this is a simple Euclidean chain rule, right? So it is 2 times A dotted with R. And then take the gradient of this. So this is the gradient of R dotted with A. I wrote it in the opposite way. So that I can take the derivative. This is 1. It is basically A itself. Is that clear how I'm doing this? I'm doing a chain rule. So this is equal negative. This 2 in here. I have dotted A dotted with R. That's a scalar, and this is a vector. This vector has to get along with this gradient, so I bring the A out because this is a constant, it doesn't care for the gradient. So it is minus 2 times A, the directional derivative in a sense, of A dotted with R. Again, do the same thing. We write this as R dotted with A instead of A dotted with R, and then that is 1, right? This is an identity operator, and this seems to be minus 2 times A dotted with A. Okay. So it is not a solution of a Laplacian. So A dotted with R is a solution. A dotted with R square is not a Laplacian solution unless A square is 0, right? So, but that's a constant. I say that we start with the structure that A is like the A was any constant here. So let A square be 0. The vector magnitude is 0 is going to be our condition, and a quiz show that in this way of doing it. And typically I like asking this in the exam because this is a short enough question. So for L equal to 2, so this was 2, for L equal to 3, work this out and show that again it is 0 if A square is 0, or it will come out in terms of A square. So calculate what is A dotted with R. So 1, 2, 3, right? Is equal. So in general, what happens is that you can calculate this and you can show in general that this is equal to 0 for any L if the vector A obeys this is called a null vector. This is called a null vector. So a vector whose dot product with itself is equal to 0. Give me an example of a null vector. A vector whose dot product with itself is 0.
I dot I 0.
0 vector.
0.
0. Sort of trivial. Because then it doesn't exist. Yeah, that's a correct solution. Anything else?
I dot I 0.
I dot
I.
I dot I is not 0, right?
Oh, sorry.
It's 1.
Yeah, I dot Z 0.
I dot j is 0. We want a vector with itself is 0. So not be possible because I spent some time on it. But it's correct that, I mean, usually we say dot product is 0 when they're perpendicular, but a vector is never perpendicular to itself. So how is it possible? the non-trivial solution. It's not a standard way of thinking. So null vector is A started with A is equal to 0. Usually if it has three components, is A1 square plus A2 square plus A3 square is equal to 0. So square of three numbers, when you square it, usually they're positive. This has to be equal to 0. Square of three.
Negative vector or complex vector.
Complex vector, right? Who says that I should be in the real plane? The A is some vector. So for real numbers, that's not possible. That's what we were all trying to physically motivate ourselves. But A can be complex, and then we have room, right? So that will be complex. So let's say A1 minus A2 is equal to Y minus square. So that's, I want to make sure that I choose this correctly. So plus actually, yeah. So plus A plus A2 is Y minus square and A1 minus IA2 equal to Y plus square. A1 and A2 are we are saying now complex, right? A1 square, A2 square, but in such a way that Y minus and Y plus are complex. Y minus or Y plus are complex. In terms of that, I can write A1, A2, and A3, and let's say A3. I have to get this all to be 0, right? There are only two independent variables because third one can be written in terms of that. What is A1 square plus A2 square? A1 square plus A2 square would be equal to square of this, right? So A1 plus IA2 times A1 minus IA2. That's the idea of complex numbers, magnitude of that. A1 square plus A2 square. But that, if this is equal to true, should be equal to minus A3 square. So A3 then is equal to, this is A1 plus I2 times this, so this should be the following. So this should be Y plus times Y minus. This gives me a minus, so let's, this is also equal to Y minus square times Y plus square. So A3, if I have it to be minus, then I'll get exactly the opposite of that. So together, they will give me a 0. So this gives me a 0. So A1 square plus A2 square plus A3 square is equal to minus A3 square plus A3 square. That's equal to 0 by construction in a sense. That clear? Questions on that? Okay, so if that's the case, I can invert it. I would also like to know what is A1 and A2. So A1 would be add these two. I have Y minus square plus Y plus square divided by 2. A2 is equal to, I add the when I add it, it was A1. When I subtract, it is square minus Y plus square over 2. This is okay. And A3 stays the same. So that's my representation in terms of Y plus and Y minus. So whenever I want to think of a null vector, I want a one possible configuration is this. This is not the only configuration. I can have null vectors in many ways, but that's one construction I can make. Okay. So this A1, A2, A3 in terms of y minus and y plus with a complex makes me is a guaranteed feature that A dotted with A will be equal to 0. If that's the case, can I erase this part? Oh, yes, question.
Should there not be an I for A3, like I y plus y minus, because minus A3 square is y plus y square.
Uh, so A1 plus A2 square. Yeah, what's your question?
A1 square plus A2 square is y plus square into y minus square, which is minus A3 square. And so the minus, when we take the square root, shouldn't that have?
Oh, shouldn't that be an I? Yeah, why is that not there? Good question. So your point is that if I were to start from here, so this is equal to y minus square, y plus square. So A3 seems to have an I in there. Yeah, why is that not there? So it seems to be inconsistent, correct? So this and this is inconsistent. Okay, help me. So let's start again. So A1 plus I2 is right. Yeah, let's start this over if you don't mind. Okay, so A1 square plus A2 square is equal to
A1 plus I.
yeah, so let me check.
Okay.
Is there a minus sign then? Oh, yeah, there's a minus. That's right.
Yeah.
Thank you. So this is equal to A1 plus A2 times A1 minus A2. Thank you. Otherwise, I will struggle at a later switch. Okay, so this is equal to A1 square plus A2 square. Totally, but that's also equal to minus of y minus square y plus y square. This we are saying is minus, yeah, I think now it might be consistent. That's equal to minus 8p square is equal to minus y minus square plus square, and now everything is fine in this. Yeah. Anything else you see? Okay, let me keep it there since that was an issue. So I keep this here. So this is my construction. This is a way to build a null vector, not a unique way, but a way to one of the ways to construct a null vector in terms of two complex numbers, y minus and minus. Okay.
So shouldn't this time A1, A2 minus shouldn't be changed, we bring another minus.
Okay, yeah.
So now we bring another minus before y plus.
Oh, here. Oh, yeah. Now this might change your direction. Yes, yes, yes. So I will say that this is minus, correct? A1, 2 times A1, and I add this is minus and this is plus. Correct. Is that correct? So when I subtract them, it becomes plus. Hopefully. Too many errors. The construction level. Oh, what happened to EM? Okay. Yeah, okay. I didn't realize. Okay. Good with me? Okay, hopefully this is all correct. Okay, so now we would like A dotted with R raised to L, right? That's the construction we are making, and this will be your generating function for the spherical harmonic. So let's talk in terms of A dotted with R raised to L. So A is equal to this vector, right? So A1, A2, A3, the three components are y minus square minus y plus square divided by 2. The second component is y minus square plus y plus square divided by 2i. And the third is y plus y minus. This is your I component, j component, k component. These are your rectangular three components, so it's a basis dependent quantity. And R vector, we use spherical coordinates, so it is the magnitude r itself times sine theta to sine phi sine theta, sine phi, and cosine theta. Let's do A dotted with R then is equal to basically multiply these quantities, correct? This times this, and so on, and then I have to take the overall raised to L. So y minus square minus y plus square divided by 2 times sine theta cosine phi plus minus square plus sine phi plus y minus y plus y minus times cosine theta. Now, our goal will be, so that's a construction, I can process it a little bit. But let's wait for that in a minute, but let me tell you what the motivation is. A dotted with R hat. Oh, there is an R, right? So there was an R in this whole thing, magnitude R. So I divide that out here, and this is nothing but R hat. So my construction will be, if I were to do A dotted with R raised to L, this will be equal to summation of L M going from minus L to plus L. Collect all the y plus and y minus. Y plus raised to L plus M divided by L plus M factorial, and there's a square root. Y minus and y L and theta phi. This will be my definition. The coefficients that sit in here, that will be my spherical harmonics, except for one more feature. There is a 4 pi over 2 raised to L, and I am always on which side it shows up. 4 pi over. So there's a 4 pi over 2L plus 1 on the right, and there is an L factorial on the left. I remember this L factorial that was adding on at various places, so I should define that here itself. So this will be my definition of spherical harmonics. So I have to rewrite this. I have to collect the terms inside in here so that I can read out what my coefficients are. That's going to be your quiz. Okay, that's a hard quiz to do, but do it. But we will do that in the lecture also. So fine. So based on this, so take this, substitute it in here, write that in terms of this, and try to get the spherical harmonic. Is the question clear? So 1, 2, right? Substitute the quiz, right? This is your quiz. Again, you don't have to spend too much time. I will be doing this in the class next time, but it will help if you come prepared. So quiz is substitute 1 in left hand side of 2, expand out. So there's a power, right? Expand out and collect coefficients of y plus raised to whatever this number is, y minus raised to whatever this number is. When you expand this, there will be powers in terms of this, this, and this. And you have to collect all the powers of y plus and y minus. A tedious job, very tedious job if you're doing it for the first time, if you don't take any assistance. It is very hard, but that's what Laplace did for us. And those collected terms are called the spherical harmonics. Okay, so that's the definition of the spherical harmonic. So maybe to make life easy, so quiz, collect the terms for, so A dotted with R hat, do this Q. So this will come out to be M is equal to, why not? Why go for a cube? Make it simple, right? 2. Right, so let's do square. So this will go from -2 to +2.
2 factorial.
2 factorial, yes, thank you. Right, -2 to +2, and this will be y plus raised to 2 plus m, and you have 2 plus m factorial. Y minus 2 minus m, 2 minus m factorial. And find this out. You have to tell me what this is. So this will be qm theta phi. A cheating would be that you can go and look for what is spherical harmonics for L equal to 2, 2, 0, 2, 1, and so on. Those are available, but I want you to expand this out. Okay. So, and you can verify that that's what will be coming out to be. So 2 pi times 2 times 2 or 5, right? So this is 5. That's what this will come out to be. If you just try this out, it will help a lot because then you will have a motivation for what is going. The insight will be very clear if you just attempt it even for 5 minutes. So this will help. And we will process this, and we will, as a homework part, we will do the completeness relation for spherical harmonics, orthogonality of spherical harmonics. All the features will come in, and we will do some examples that you can apply. Okay, I'll stop here. So, Fuzel, you came late.
Yeah.
Yeah, so I was saying that I was very hard on grading the exam. So, but I'll be very extremely lenient on grading the homework part of the exam. So it is 60% for take home, 40% for the in-class. Okay, so that's all. That is the only thing important you missed, I suppose.
Oh, you're not going back in for some reason.
Yeah, I think.